All right, just a quick test. Can everyone hear me just fine? Perfect. All right. Let's get started then. Let's see here. Be gentle. Okay. Well, I'll try. I don't know exactly how gentle physics will be, but I'll certainly try to make it as easy as possible. All right, I'm going to test out the video real quick. All right. Everything look good? Let me know. Okay, perfect. All right, then let's get started. Oh, thank you. All right, so there are 27 questions I made on this, with some emphasis on conceptual stuff. Yeah, thank you. I love decorating my rooms, changing based on the seasons, so. And you're welcome for this session. I enjoy doing what I do, so glad to help. All right, so let's take a look at number 1. This is all in topic order, by the way, so we're starting with magnetism, magnetic flux. So we have 100 circular loops of wire with an area given. It's 50% immersed in a region containing 0.25 Tesla magnetic field. It's out of the page, as shown here, and there's nothing outside the region. So what we mean is there's this region I've boxed in right here, and there's a magnetic field inside of it, and there's no magnetic field outside that box. Now this loop here is a circular loop, but only 50% of its area is inside of that box. So half of it contains magnetic field and half of it doesn't contain any magnetic field. We want to find what the magnetic flux through the loops are. Now, for this one, okay, let me make sure the camera's focused. So let's see here. Number 1. Okay, and then just let me know if there's anything that doesn't look clear. If you need me to use a different color or anything, just throw anything you have into the chat, including any of your questions. So for number 1, I'm going to have this magnetic field, which is coming out of the page, represented by the dots. Okay, so there's my region of magnetic field. And that green is probably not the greatest. I'll probably not use in the future. But you have this loop, which is halfway inside. There's actually 100 circular turns of wire. Now the thing is that I told you that there's multiple turns of wire, but it doesn't matter here because the flux doesn't depend on how many turns of wire that you have. So the magnetic flux is based on the magnetic field strength B, the effective area as we call it, which is the area that contains magnetic field, and then some orientation, so it's the cosine of some angle. I like using phi. It's usually written as theta. Now, the effective area, you have to remember, doesn't have to be the area of the entire loop. It could be only half of the area in this case, which is just the area that contains the magnetic field. So in here, the angle, okay, so this is the angle between, if you want to call it the area vector and the magnetic field vector. So what I mean by area vector is basically which way the area faces. So if you have this loop right here that contains some area, the area can be facing one of 2 ways. If you were to imagine that there was like a face on it, okay, so if you pretended that there was a face on that, that face would either be facing, in this case, out of the page, or it'd be facing into the page. You can pick either or. It's best to choose it in the same direction as the magnetic field to make it simpler. So given that this faces out of the page and the magnetic field also points out of the page, those two directions are aligned, which means the angle between them are 0. So if the angle is 0, then the cosine of that angle is 1. So in most cases, when you're dealing with the flux, at least in this class, you're either going to have this result be 1 or 0, basically, meaning you either have a maximum flux that's facing with the magnetic field, or you have no flux, which is if it's perpendicular. It's basically going to be one of those two cases most of the time. So the flux simply reduces down to B times A, and we just plug that in. So the magnetic field strength in this case is 0.25 Teslas. And our area is directly given. It's 0.10 meters squared. Okay. So in this case, you can just calculate that out, and it's just 0.025. You can leave it as Tesla meters squared, or it's the same thing as a Weber, so abbreviate WB. Okay. So the answer is 0.025 for that. Let me know if you have any questions on this, otherwise we'll move on. Would you... Oh, you're right, sorry. I got a little too eager with that. So you actually need to cut in half the area for that because we're only using half the area. So I mentioned that, but I didn't actually cut it in half. So you're only going to use half that area. So that means for this area, you need to use 0.05. So this actually is 0.0125. Now actually, based on that, because when I wrote the problem, you'll actually notice I don't think it's one of the correct options. Let me see here. We have 0.025, 0.0008. Yeah, so actually in here, it's none of the options actually. So that's my bad. Yeah, so when I made this, I forgot to halve the area. So you can write in the little E, none of the above for that one. Any other questions on this one? Okay, let's move on to the next one. So again, use half the area and ignore the number of turns of wire because it's not included in magnetic flux. Now the turns of wire may come into play somewhere else. So if you'd use Faraday's law, you'll talk about the number of loops, which is indicated by N. So just not in that case. In this one, we have 5,000 loops of wire. The diameter is given. They're immersed completely in a 50 microtesla magnetic field. So I have these two pictures here shown. Basically, they represent two different states. So initially, the magnetic field is aligned in the plane of the loops. You can see that here, the magnetic field points directly up in the first diagram, but the loop faces in or out of the page, which is perpendicular to that. Now, it's rotated 90 degrees into its final orientation, so that's what the second picture is for. Now the loop is oriented facing out of the page, and the magnetic field is out of the page, so they're aligned with each other in this case, whereas in the first case they were perpendicular to each other. We have a given time that elapses. We want to find what the magnitude of the measured voltage in the loops is. So for this, you should recognize that because there is a change in the magnetic flux, you want to use Faraday's law to calculate the induced EMF or the voltage. So for this one, So we have for 2, it's Faraday's law, which states that the magnitude of the induced EMF or the voltage is the number of loops or coils you have and the change in flux, which is the most important part, and over a change in time. Okay. I'm taking the absolute value of this and ignoring the minus sign because it's a voltage, and whether if it's plus 12 volts or minus 12 volts, that voltage difference is still the same. It's just if you want to view it one way or the other. The minus sign only has to do with the direction that the current will ultimately flow, and that you'll figure out with Lenz's law if you want to talk about that. So we just want to get the magnitude. Now we're going to focus on getting this change in flux first. So I'll calculate this first. The change in flux is flux final minus flux initial. The change in anything is final minus initial. Now, in our 2 pictures, we have 2 extreme cases. So in the initial situation, the magnetic field is oriented vertically upward, and our loop essentially faces, if you want to call it out of the page, you could do that. Into the page or out of the page, it doesn't matter. The angle between them is 90 degrees. So if you can see this, that the loop is oriented in such a way that the magnetic field skims it and it does not actually go through it. So these magnetic field lines do not go through the loop, means there's no flux. So no flux initially. You could write the equation out, but you would use 90 degrees, and cosine of 90 is 0, which is why we get no flux. So essentially it's no flux given. Now, you rotate the loop by 90 degrees in such a way that the magnetic field looks like it's oriented outwards now. And you have your loop. The loop is facing in the same way that the magnetic field is, so there is magnetic field passing through the loop, so there is flux in that case. So when we calculate the change in the flux, we can cross out the initial flux because there is no flux to start with. And we calculate the flux final by just using the equation for the flux. So the flux final is the magnetic field final, the area final, and the cosine of the angle final. But again, since they're aligned in the same direction, the loop faces out and the magnetic field points out, the angle between them is 0. So the cosine of 0 is 1. So we can just ignore the cosine. Now, for the rest of this, we just plug in the magnetic field strength. So the magnetic field strength is 50 microteslas. So you have to change the micro into the standard unit. So we get rid of the micro by saying it's 50 times 10 to the minus 6th teslas. So that 10 to the minus 6th would be your micro. Times the area. We have an area which we have to calculate based off of the diameter. So since we have the diameter, you have to cut it in half to get the radius. You could also use a formula for the diameter to get the area of the loop, but since most of us remember pi r squared, we need to cut the diameter in half. So we need to do pi times the radius, which is half the diameter. So we do 10 centimeters, which is 0.10 meters. Don't forget to square it, and then calculate that. Let's see here. Questions. Can I repeat why there's no flux in the first loop? Okay, so to reiterate why there's no flux in the first loop, let me grab a piece of paper. Okay, so pretend that this piece of paper is basically where the loop resides in, so the loop is in the plane of this paper. Now, let's say that the magnetic field is coming straight at you, okay? So if the magnetic field was coming straight at you, it would pierce through the paper like this, and that would be the flow of a magnetic field through an area. That is flux. Now, if the area were oriented like this, so it were flat, and the magnetic field skims along the surface. It doesn't go through it, so it only skims along the surface. When the magnetic field skims along the surface, it doesn't go through it, that means there's no flux. You have to have magnetic field passing through it. So just by looking at this, magnetic field skims it, no flux. And then no flux because loop is perpendicular to the magnetic field. You have to be careful about how you choose to say perpendicular and parallel. So the orientation of the loop is perpendicular to the magnetic field. That is correct. So the loop faces out of the page while the magnetic field points up. However, sometimes people also like to say, oh, you know, the plane of the loop is perpendicular to something, which is a completely different statement. But based off of the stuff that I've been saying about which way the loop points, it is perpendicular to the magnetic field. Now, we calculate this out. 0.10 squared times pi times 50 times 10 to the minus sixth. Okay, so I'm going to put this in scientific notation because it's a very small number. So our flux is 1.57 10 to the minus sixth. I'll write it in Webers because we have Tesla meters squared. Now, we take that flux, that is the change in flux, okay? We plug that into here along with the other things and we get our induced voltage. So the induced EMF or voltage is number of loops. In this problem, it's 5,000, no units. And then we have a change in flux of 1.57, 10 to the minus sixth Webers, divided by the time that we're changing this over, which is 0.01 seconds. Okay. And we calculate this voltage to be, so we take that number we just got divided by 0.01 and we multiply by 5,000. Okay. So for this, don't need it in scientific notation because the number is not that small. The voltage is 0.785 volts. Okay. 0.10 is the radius of the loop. Yeah, good. Glad you are all participating and helping each other out here. Are there any other questions for this particular problem? All right, no problem. Let's go to the next one. Okay, so on this practice test, I chose to group questions with one overall prompt, just simply because there's a few things that you could ask about some of these, especially what we're going to do now. So with this one, you have a conducting rod that slides to the left in this diagram. So this rod right here slides to the left. It's completely immersed in a uniform magnetic field. So in this case, you can see that there's a bunch of X's, so it's directed into the page. And we're doing questions 3 through 6 for this picture right here. So the first thing is there a change in external magnetic flux? And how is it changing? So if you kind of skim through questions 3 through 6, these are all questions that actually pertain to Lenz's law. These are all of the individual steps that lead you to the final result, which is which way the current flows. So we're going to start with, is there a change in external magnetic flux? So in this case, because the rod is sliding to the left, we see that there's an area that is enclosed here creating this loop with the rod. This area shrinks, decreases in size. So that means if you have a change in the area, and flux depends upon the area, as well as a couple other factors, then you should know that there should be a change in external magnetic flux. How is it changing? Well, the area is shrinking. So yes, it's decreasing. Everybody see that? Okay. I thought it decreases when it moves away. No, so for this, let me write this out here. How do we know it's shrinking? Okay, two similar questions. So let me write this out here. Now, if you thought it couldn't get any more confusing, I already have a question that I'm preparing for the third version that we'll go over tomorrow during our last review session. So we'll have some fun with that. It has to do with how the area changes. So for this one, so when you have this here, so what we're saying is that there's this conducting rod that connects between the two ends, and it completes this loop here. So what I'm paying attention to in this picture is this section right here. You know, there's a little bit of extra, you know, conducting track that extends out to the right, but here is the loop itself. Okay, so as this rod, this particular piece moves to the left freely, okay, while the rest of it stays glued into place. So the only thing moving is this rod. As it moves to the left, you're going to be using the area that's enclosed in this loop. Okay, but as you move that rod to the left, that area continues to shrink until when the rod reaches all the way to the left side, there is no loop anymore because there's no area left. So we know that as the rod moves left, loop shrinks. Okay, so the area is going down. Now, because it relies on a change in flux, if you write that the flux is based on these factors, so it's based on your magnetic field strength, the area of the loop, and the orientation of the loop. If you change any of those three factors or multiple of them, then you'll change the flux. Now in this case, because the area is shrinking, this area shrinking means the flux decreases. There's less area for the magnetic field to pass through. Hopefully that makes sense. If the rod moves to the right, then the area gets bigger, which makes the flux increase instead. So the loop is shrinking because the bar is moving closer. So the bar is moving closer to the left side. So if you treat that loop as a rectangle, the right side of that rectangle is moving closer to the left side, to be very precise. Okay, so yes, it is decreasing. 4, if the external magnetic flux is changing, which it is, why? So we have a few reasons here. So one is based on a change in magnetic field strength. Another way is it's based on a change in the effective area containing magnetic field. And the last way is that there is a change in magnetic flux because of a change in the angle between the magnetic field and the loop. So these are the three factors in the equation I just mentioned. Basically, which one is responsible is the change in the effective area, because the area shrinking is causing the change in the flux. So the answer is B for that one. Five, which way will an induced magnetic field inside the loop go? So this has to do with realizing that there is a secondary magnetic field that is created within the system that will try to oppose the change in the external field. So let's take a look at this. So we have this external magnetic field that will draw out. It's into the page. So we have this field going into the page, represented by these X's. Okay. Now, these all represent what's called the external field. When we use the word external, we mean something that's external to this loop system, something that's outside of the picture that we don't care about, but it's coming from another source. Anytime you're referring to internal, it means something that's part of the system itself. So technically what I mean is that there is an internal magnetic field that is created, which we're calling the induced magnetic field, because it's induced as a result of a change in the external. What I'm saying is there's a magnetic field somewhere in here. We're going to either say it's into the page or out of the page, depending on how we're going to oppose the change. So Lenz's law, very briefly, I'll state that it's that an induced magnetic field or flux is created in such a way as to oppose the change in the external. This can be stated in multiple ways, but I'm writing it in terms of magnetic field and flux. So we understand that this magnetic field or flux points into the page, the external one. But we know that the flux is decreasing because the area is decreasing. So whatever we have going into the page is being taken away. It's decreasing. But Lenz's law says that it'll create something to oppose that change. It will prevent it from happening. So if it's being taken away, it's going to do something to keep it there. So you have two options. You can point something out of the page, or you can point something into the page. Now, if you're trying to prevent it from being taken away, then you need to point something in the same direction. Because think of it as this vector that's pointing into the page and it's shrinking in size. In order to help it grow back, you have to point something in the same direction to keep it from going away. So you say there's a bunch of X's inside of here, and that is called the induced magnetic field. The other thing that could have happened was if we said that the flux was instead increasing into the page, we would have said to point something out of the page to keep it from increasing. So remember, you're opposing either the increase or the decrease. I know that's one of the most confusing ideas, so if there are any questions on that, let me know. Okay, so for this one, the answer is that the induced magnetic field goes into the page. And you need to just repeat on the last part. Okay, so the last part I was referring to, I think I was mentioning how if you had the other case, so if in this system, if for some reason the flux was increasing instead of our case, which is decreasing, if the flux was increasing, then you would try to decrease it to oppose that. So in that case, you would have pointed something out of the page to counteract the increase. That's what I meant by that. But in this case, it's a different story. No problem. Okay. 6 is the last step. So once you've solidified that, 6 is actually relatively easy. Which way will a current flow through the rod? So I'm asking you particularly through just the rod. So if you go back up to here, now you have, let me actually just go to my diagram because I already have everything on it. Now, you're going to pay attention to the induced magnetic field because the loop creates a current which creates this magnetic field, the induced one. Remember, that's the one that's internal to the system. So you have to use your right-hand rule here to figure out which way the current flows based on this induced or internal magnetic field. So you can easily stick your thumb in the direction of the induced magnetic field and the direction that your fingers wrap around, which is in this case clockwise. That's the direction of the induced current. Now, you may notice that I gave you word choices such as clockwise and counterclockwise, so the answer for the whole loop is clockwise. That's if you're referring to the whole loop. But if I ask you through just the rod alone, the current doesn't go clockwise through one piece of the loop. This part of the loop, the current can only go down. So the answer for the current through the rod is down to be consistent with clockwise. So it's down. I see you all trying to answer B. Yes. Oh, the answer to 4. Yeah, the answer to 4 was B. Yeah. Can we assume increasing flux means opposite directions and decreasing flux means the same directions? Increasing flux. Yes, that is a fair assumption, because anytime you are trying to increase the flux, whichever way that external magnetic field points, if it's being increased, trying to oppose that means you need to decrease it, which ends up being in the opposite direction. But then in our case, since it's a decrease in flux, we point something in the same direction to keep it from decreasing. So we are attempting to increase it to counteract that. So that is a fair assumption. Is the answer to 6 D or A? So if I told you which way will the current flow through the loop as a whole, so which way does the current flow through the loop, the answer is clockwise. But in our case, since I'm asking you for what the current is through just the rod, the answer is D, down. All right. If there's any other questions, let me know. Otherwise, we're done with that one, and we'll move on to Transformers. Not the movie. I mean, you can make a movie about this, but it probably wouldn't be very exciting to many people. So for questions 7 through 9, so these 3 questions here. You have an AC source. Okay, so we have the symbol which indicates an AC source. Has an RMS voltage of 12 volts. So remember to distinguish between the root mean square, the RMS, and the peak or maximum value. There's a relation which is based on a square root of 2. It's a very simple one, but you want to remember that. In this case, I give you the RMS voltage. It's connected to a transformer with 10 times more turns of wire on the secondary coil compared to the primary coil. So remember when we use the terms primary and secondary, primary is referring to the input. So the input is on the left side, that's the primary coil, and the output is on the right side, that's the secondary. Now we have more turns of wire on the secondary coil, 10 times more. I want to know how much voltage will be across the secondary coil. So if you know the simple fact that the number of coils pretty much determines the voltage, in other words, more coils translates to more voltage, then 10 times more coils actually means 10 times this voltage here. So the answer is that the voltage on the secondary is 120 volts. You can easily get that with the equation too, because the equation that you use for the transformer just states the ratio between the two. So for transformers, you have that the voltage on the primary divided by the voltage on the secondary is the number of turns on the primary divided by the number of turns on the secondary. So in other words, because there are 10 times more coils on the secondary, the number on the bottom for the voltage should also be 10 times larger than the one on the top. So if you end up solving for this, so V secondary equals, we're going to just flip this around. So I'm going to flip this over to the other side. So it's NS over NP times VP. So you solve for the voltage on the secondary. Well, it doesn't matter exactly what these numbers are, as long as you know that this one's 10 times bigger than that, then what we're saying is the whole thing is just a factor of 10 times 12 volts. Okay. If you chose to put 1 on the bottom, then the top will be 10. If you chose to put 10 on the bottom, the top will be 100. That ratio will never change. So it's always going to be 10 inside here, no matter what. So you get 120, and that's the answer. Number 8, if an average of 10 watts of electrical power is delivered into the primary coil, how much power is outputted by the secondary coil? This is a very simple one if you understand that the energy is conserved. Power is just energy over time, so whether if you're talking about energy in joules or power in watts, the energy is conserved. So that means 10 watts input equals 10 watts output. So the answer for this one is 10 watts. Okay, so number 9. Consider that the AC source is replaced with a DC source. So AC is alternating current, DC is direct current. So we have alternating as it flips between one direction and the other for the current. Direct current means that the current that doesn't change at all, stays the same direction. We replace it with a DC source with the same voltage of 12 volts. How much voltage will be across the secondary coil? So the thing is that because if you look back at the diagram, okay, so this is a rough representation of what a transformer would look like schematically. The thing is that you have the input side, and here's your primary coil, and it loops back over here. So this is one complete system right here. Now, this thing right here, if you want to know what it is, it's basically an iron core. It's something that will channel the magnetic field to the other side, but it's not something that directly transfers your voltage or your current from here to here. It only channels the magnetic field over to this side, and the change in the magnetic field, because it's alternating, induces something on the other side. So it's an induced current and an induced voltage on the right side. The thing is that in order for something to be induced, something has to change. So the thing is that if you replace this AC source with a DC source, there's no change in anything. So if you don't have a change in the magnetic field that goes over here, then there's no voltage induced and there's no current induced. So the answer is that nothing happens on the right side because it's DC in that case. So in this case, we get 0 volts on that. And if you were to also answer what the current is, it's also 0. Can you repeat about the input and output of watts? So on number 8, what I meant was that because the energy is conserved, it stays the same value on both sides if you talk about energy or power, because energy and power are pretty much the same thing. Power is just energy per amount of time. So if the energy is the same on both sides, the power is the same on both sides due to conservation of energy. Any questions on one more question? In other words, transformers don't work with a DC source because there's nothing changing. Correct. DC source implies that you're keeping it at a constant voltage and constant current, which means that, again, when you go back to here, when you have a solenoid, which is just a bunch of turns of wire, a current creates a magnetic field. So if you don't change the current, you don't change the magnetic field or the flux, which goes over to here. So no change in flux means nothing is induced over here. This exam, the blank copy or the solutions, because the blank copy I'm using right now is already on Canvas. The solutions will be up sooner or later. I'm hoping I can get it up tonight, but we'll see. Any other questions on 7 through 9, and then we'll move on to the next section. Yes, you can rewatch this later. So you'll need to give it a little bit of time. So as soon as I hit close on the live stream and I end the live stream, it takes at least a couple hours for YouTube to actually throw the upload up. So if you end up staying up really late, then you could rewatch it later. Who knows? I have no clue. Otherwise, you'd have to wake up tomorrow morning to rewatch it. Okay, so let's take a look at numbers 10 through 13. So we have an RLC series circuit, has an AC source, outputs an RMS voltage of 120 volts. The resistor has a value of 300 ohms for its resistance. We have reactances given. Now, notice that in the prompt, I do not tell you what reactance belongs to which. I tell you that there are two reactances of 800 and 1200. That's it. Okay. So do not make any assumptions about that unless it's directly stated. Suppose that the resonant frequency of the circuit is a known value and it's 60 hertz, while the circuit is driven at 120 hertz. So the resonant frequency is that frequency at which there's a few things that you'll know to be true. The circuit does not need to be driven at the resonant frequency. You can drive the circuit at any frequency that you want, which in this case we're driving it at 120 hertz. We just happen to know what frequency it would resonate at if we were to be at that frequency. So, given all of this information, 10, what is the reactance of the inductor and the capacitor respectively, meaning in the same order I listed them in? So you'll notice that all answers have two answers to them. Okay, and the answers that I list out will be corresponding to first the inductor and then second the capacitor. So how do we know which one belongs to which, or is it neither of them? So the thing is that you know that the inductor and the capacitor behave differently at two different frequency ranges. So we're going to refer to them as high and low frequencies. Remember that the inductor responds to changes in the current. Look at when we went back to the transformers, we were talking about how changes in the current cause a change in the system, which induces something. So when you have changes in current in the inductor, then it's going to oppose the change. That's its nature. So the more you change something, the more the inductor is going to oppose it. So as you change it more often, in other words, run it at a higher frequency, it opposes more and hence blocks the current more. Remember that reactance is a measure of how much it will essentially resist or block the current. So at high frequencies, the reactance of the inductor is higher. Meanwhile, the capacitor, now the capacitor stores charge on its plates as opposed to permitting current through its coils for the inductor. As you store more and more charge on a capacitor, as it fills up, it's less willing to accept charge. So as you fill it up completely, the current shuts down. So we say that the reactance is higher when you allow it to charge up more fully. That happens when the frequency of this circuit is lower, because when you run this at a low frequency, that means that the current will run clockwise for a little while, and then it'll run counterclockwise for a little while, and it will go back and forth more slowly. So if you run it at a low frequency, it will fill up more and it'll block the current more. So the reactance is higher at low frequencies. Now, those are good conceptual ideas to understand. Notice that our resonant frequency is 60 hertz and we're driving it higher than that. So if we're leaning towards higher frequencies relative to what the resonant frequency is, running it at higher frequencies means that the inductor blocks it more than the capacitor does. So the inductive reactance should be bigger than the capacitive reactance. So in other words, the 800 ohms and the 1200 ohms I gave you for your reactances, the inductor reactance is 1200 ohms. So the answer is C. Inductor is 1200 and the capacitor reactance is 800. Okay, so it has to do with, are you above, at, or below the resonant frequency? And that's what you're going to label as, are you at a high frequency or are you at a low frequency? Are there any questions on that? Okay. Looks good so far. For 11, we're going to suppose that the angular frequency of the AC source is decreased slightly. Now, when I say angular frequency, that's omega. However, you'll notice that the angular frequency goes with the regular frequency f that you use. The angular frequency is equal to 2 pi times f. In other words, so as long as you're just discussing whether if the frequency increases or decreases, the angular frequency goes exactly the same way. There's a question, if at the resonance frequency, what would change? So if I were to talk about number 10 in context of being at the resonance frequency, so in other words, if I drove the circuit at 60 hertz to match the resonance frequency, then the reactances would be equal to each other. So in fact, the values would not be 800 and 1200. I would have told you that they would have been two different values from what they are now. That would have been, so it would have been like, let's say it was 1000 and 1000. The point is that they would have matched. In fact, I wouldn't even really need to tell you that it's at the resonant frequency in the problem for you to know that if the reactances are equal to each other, it's at resonance. But if you're putting it in context of number 10, if you were at resonance frequency, well, then they would both be the same value. So it would have been B if it was resonance. Could you repeat how you corresponded the values with the capacitor and the inductor? So again, real quickly here, how I knew that each one of these belonged to either the capacitor or the inductor was simply if I knew that I was driving the circuit at a higher or lower frequency. So remember that driving the circuit at a higher than resonance frequency, which is 120 compared to only 60, driving it at a high frequency will cause the inductor to react more. Now, if you want to use your equations to actually just do this, if you don't remember it conceptually, you can use the equations to determine this, because the reactances for the inductor, XL, is omega times L, where omega is the angular frequency, and XC is 1 over omega C. Notice the nature of these is that they're opposite to each other, where this one, if you were to increase the frequency, you get a larger reactance out of it. Whereas here, if you increase the frequency and it's in the denominator, the whole thing becomes smaller, so the reactance gets smaller. So you can also use the equations to figure out which one has the larger reactance. So because we're running it at 120 hertz, which is larger than the resonance frequency, so we're going higher in frequency. Going higher in frequency would mean that for the inductor it has the larger reactance. So we would say that the 1200 belongs to the inductor and the 800 belongs to the capacitor. Hopefully that makes it a little bit more clear and you can see it from at least two different perspectives of how you arrive at that conclusion. I'll finish all the way up through 13, and then we can, if there's any more questions about that, I can go back to that. For 11, we're going to suppose that we have that the angular frequency of the AC source is decreased slightly. So when I say slightly, I mean you're not changing it by much, but it is decreasing. What will happen to the RMS current through the circuit? So this one you have to understand how the current works in the circuit in regard to your reactances and the resonance frequency. You have to remember that when a system is at its resonant frequency, so whether if it's circuits or if you're talking about like a swing set that's swinging back and forth and it has a certain frequency at which it oscillates, any system that has a resonance frequency will give you the largest possible output at the resonant frequency. So if we're talking about current output, okay, the current that runs through the circuit is going to be its largest when it's at the resonant frequency. So the thing is that we're running it at 120 hertz at a frequency which is larger than resonance. If you get closer to the resonance frequency, then the current actually gets larger. So by decreasing the value of 120 hertz to a value which is slightly less, but closer to 60 hertz, we are getting closer to resonance, and that makes the current output larger. So it will increase. Now, if you learn a little bit more visually, I'll give you a little graph for that. This is the graph, how the graph looks like. This is a graph of the current output in the circuit versus the frequency F that you're running at, but you could also say omega too, because the angular frequency goes with the regular frequency. But this graph looks more or less like this. Okay, it's basically this peak, single peak on the graph, and the peak current, the largest value of the current here, I maximum, corresponds to your resonant frequency. Okay, so in our situation, because we were running at 120 hertz, maybe, 120 hertz might be somewhere over here. Okay, so let's say we're right over here on this graph. We get some current, but let's say at resonance, which is 60 hertz, which is lower, if you move from 120 hertz any closer to 60 hertz, the current output goes up until you reach resonance. Now, if you were to go past the resonance frequency, it would then just go back down, because then you're going further from it. So, all right, for 12, suppose that the driving frequency of the circuit is changed again. Okay, so we changed it in problem number 11. We're going to change it one more time. So, and it is found that the impedance of the entire circuit is 300 ohms. Is the circuit now being run above, at, or below the value of the resonant frequency? So we know that the impedance is 300 ohms. Now remember that impedance is the collective overall effect of all your reactances and all your resistances. Because remember, reactance is kind of like resistance in a way. So impedance is just putting it all together. If you want to recall the equation for impedance, the impedance, Z, is the square root of R squared plus the difference between XL and XC squared. Okay, so that's impedance. Now, if you know that the impedance is 300 ohms in our case, so we know that the value of this is overall 300 ohms. Go back to the values that I gave you in the problem. The values I gave you in the problem consisted of a resistor with a resistance of 300 ohms. That alone should actually already tell you something, but I also give you the reactances as well. Now, notice that if the resistance is 300 ohms and the impedance of the entire circuit is also 300 ohms, well, guess what? That means that in the rest of this equation here, all the stuff pertaining to the reactances, it has to mean that this entire term goes to 0. Because if this one is 300 and you're getting 300 out of this, if you put any value in this parenthesis that's not 0, then you're not going to get 300. You're going to get a number larger than 300. Now, notice that this only occurs when, so if x sub L minus x sub C is 0, that must mean that the reactances are equal to each other. Okay? And that only occurs at resonance. Okay. So, because the impedance is 300 ohms, which matches the resistance value, we know that we're at resonance. So over here, the answer is that the driving frequency is equal to the resonant frequency. The other two options are basically if you're running in one case or the other, high frequencies or low frequencies. So if we were to ask the same exact question back, if we go all the way back here, our reactances were not equal to each other. They were 800 and 1200. So we knew that we were not at resonance, even if I didn't give you the frequencies. Now, because the inductive reactance is higher, being 1200 ohms, you know that you're running at a frequency which is higher than the resonance frequency at the very start of the problem. But in this part of the problem, you're driving it at the resonance frequency. So just to summarize, if you had option A, the inductive reactance would be larger. Option B is when they're equal to each other. And option C is when the capacitive reactance is larger. Are there any questions on anything related to 10, 11, or 12 before we finish the last part of this? No questions? Okay, let's do 13. What is the maximum instantaneous voltage outputted by the AC source? So I gave you a voltage. That voltage was an RMS voltage of 120 volts. I want to know what the maximum is. So the very simple relation for that is that the RMS value of anything, so in this case voltage RMS, is the voltage maximum or peak divided by the square root of 2. So if you want to write it this way, or this is the same thing as writing V RMS equals square root of 2 over 2 V max. They're both the same thing. So if I want to get my maximum, V maximum is just V RMS times the square root of 2, which is 120 volts. Square root of 2 is 1.4, roughly, especially if you're you know, taking the MCAT or something like that, if you're going that route, then it's useful to be able to round certain things. This ends up being about 170 volts. So it's 170 volts. So if you're talking about like you plugging stuff into the wall at home, that power outlet at home is typically run at 120 volts RMS. So that means that the peak voltage it reaches is actually 170. There is a question. You were talking about number 12. When would A be true for number 12? So actually, let me write these out real quick here, just so you can have them written out. Okay. So here's a few useful things. So when X sub L is larger than X sub C, so when the inductor is reacting more, you have that the frequency that you're driving at is larger than the resonance frequency. So whenever you see F naught, it's representing the resonance frequency, whereas F is the driving frequency. When they're equal is when you're at resonance, and when the capacitive reactance is larger than the inductive reactance, you're running at a frequency which is less than the resonant frequency. So this is how I would summarize the whole thing. But when you do this one, the resonance frequency, you should also know that the impedance, which equals this, will actually just cancel out this term because they're equal to each other at resonance. So that means the impedance is equal to the resistance at resonance. So this summarizes what you should know conceptually about what ranges of frequencies you're running the circuit at. So again, the subscript F0 or F naught represents the resonance frequency. So F naught is defined as the resonant frequency. Okay. And if you want the equation for that, so if I asked you to calculate out the resonant frequency, that can be pretty easily done, given that you know what the values in your circuit are for the capacitor and the inductor. So the resonance or resonant frequency is 1 over 2 pi square root of LC. Okay, so you can use this to figure out the resonant frequency, but it's given that you need to know the value of L, which is the inductance. And the inductance is measured in henries, abbreviated with H. And the capacitance is measured in farads, abbreviated by F. Okay, so those are all your standard units to calculate that. All right. No problem. Okay, so now we're done with 13. That answers all the questions for that. We're moving on. 13, we only have 26 or 27 questions, so we're halfway there. Oh, we're halfway there. So 14. This is dealing with electromagnetic waves. We have light with a given frequency of 97.1 megahertz. If that number is strangely familiar to you, you might know where we're going with this. Determine which of the following is a possible portion of the electromagnetic spectrum that this is from. So there is a little bit of information I give you below. I tell you that there is a corresponding color with some wavelength. So for instance, violet is in this range, blue's in that range, etc., all the way to red. So I'm only giving you information about the visible part of the spectrum, red through violet, okay? I give you the wavelength in nanometers, so you have to be able to compare it to a wavelength in nanometers, whatever you do. So to answer which one of these is the correct portion of the electromagnetic spectrum for this frequency, or at least a possibility, you need to figure out what wavelength this frequency corresponds to. So even though I never asked you to find the wavelength, that's the only information you have from this problem. Unless you've memorized all the ranges, which would be a little impressive, that's the only way you can figure this out, but watch how we can figure this out with just this information alone. So what we're going to do is we're going to calculate the wavelength from this frequency first. So, very, very simple equation for that. So we just use the wave equation for light. So for electromagnetic waves, in other words, light, we know that the speed of light, c, is 3 times 10 to the 8th meters per second. And that speed of light is related to the wavelength and the frequency given by this equation here. Okay. So we're going to solve for the wavelength lambda, so we're going to divide off by our frequency. So the frequency divided off, lambda equals c divided by f. So the speed of light gets plugged in, 3 10 to the 8th meters per second, divided by frequency. The frequency is 97.1 megahertz, so it's 97.1, but we need to convert the mega into a standard unit, so we need to say times 10 to the 6th hertz. You can also write hertz as 1 divided by seconds, which will show that the units cancel out to meters. So that's 97.1 megahertz. And we calculate this out, and we find it to be, so 97.1, 10 to the 6th, that's on the bottom, and then the speed of light on top. And we get 3.09 meters. Okay. So now, notice that this wavelength is, this wavelength could fit between, maybe a little bit past the span of my arms, okay? It's a pretty big wavelength compared to a lot of the wavelengths that we deal with. So like visible light is in nanometers. We can't see that small of a wavelength with our eyes. So if you look over to here, and we compare our 3.09 meters to, in this table, you notice that since everything is in nanometers, the answer does not fall inside of this table. So you can automatically say that it cannot possibly be visible light. It has to be on one end of the spectrum or the other end of the spectrum. But now you can also eliminate a half of your answers, because one way will be smaller wavelengths and one way would be larger wavelengths. So you should recognize that ultraviolet, as well as X-rays, which are not listed here, and gamma rays, those are all wavelengths which are smaller than visible light. So if you're talking about visible being nanometers, if these are smaller than nanometers, then that's the wrong direction to go towards a whole number of meters. So it's either got to be infrared or radio waves. However, infrared, or if you talk about ultraviolet light, these two ranges sit just outside of visible. So you could already say that since they're so close to visible, it can't be infrared. It has to be radio waves, because the wavelength is significantly larger than visible light. So the answer is radio waves, which is why I was hinting at this number. So if you recognize this number, you can already see why it's this answer here. Does anybody listen to that radio station? Oh, 93.1. I tend to listen to more pop, hip hop, and dance, so that tends to appear on 97.1 and some other ones that I have too. Any other questions on electromagnetic waves? Okay, so let's move on. Got a lot of people watching, almost half the class. Bravo. I guess it's pretty easy for you to all just sit at home and watch comfortably, so makes sense. So questions 15 through 17. So this is a polarizer system. Okay, so let's go into this a little bit more in depth. So these questions deal with the percentage of the light that exits out. Now, even though in these questions I'm asking you for percentages, we could ask you for exactly what the intensity is, and it's very easy to calculate it. So if anything, I'm actually asking you the harder question, which is the percentage. So I'll show you how you deal with that. We have initially unpolarized sunlight with an intensity that's given 1,000 watts per square meter, enters into a system of polarizers. So you see there are 2 polarizers in the system. The transmission axes are shown as dashed lines. So for instance, on this first polarizer, you can see the dashed line goes perfectly up and down. It's called vertically polarized. So the light passes through the first polarizer with a vertically oriented transmission axis. The second polarizer has its transmission axis tilted at 60 degrees with respect to the horizontal. So the horizontal, wait a second, is that a typo? I might have meant to say vertical on that, because the answers I wrote were based on a very specific value. Cosine of 60 is a half, I think. Yeah, change the word horizontal to vertical. That's actually what I wanted to do. So use that as vertical. Now, so this polarizer has transmission axis 60 degrees from the vertical. So what that means is if you draw the vertical line, the transmission axis is 60 degrees away from that. Another way of wording that would have been 30 degrees from the horizontal. So this first question is, what percentage of the intensity compared to the initially unpolarized light remains after the light goes through the first polarizer? So for this, you want to remember that when you go through a polarizer and the light is initially unpolarized, goes through a polarizer and it becomes polarized, the answer is very simple. It just cuts in half. That's it. So we say that the intensity out equals the equals 1/2 of the intensity in if you're going from unpolarized going to polarized. Okay. So in this case, you could say one of two things. So let's just say if this is my system here. Let me draw my polarizers. So this one has a vertical axis. This polarizer has an axis which is tilted at 60 degrees from the vertical. So if I drew the vertical line like this, the angle between the vertical and that axis is 60 degrees. Okay? So for this one right here, let's say that the light that comes into it, this initially unpolarized light, which we represent often by drawing these double-headed arrows in every single direction, because the polarization of light has to do with which way the light is oriented with its electric field. So if you say the light is vertically polarized, it means the electric field oscillates vertically. So if we have unpolarized, and when it pops through the polarizer, it will polarize it. Now, the output will be light that has the same orientation as the transmission axis. So we get vertically polarized light with a vertical transmission axis. So it becomes polarized. So between here and here, if I call this intensity I0 and I call this intensity I1, what I'm saying is that based off of this equation, we're just going to write that I1 is 1/2 of I0. There's two things you can do. You can either, one, plug in the value of your intensity, which we said initially it was 1,000 watts per square meter. So 1,000 watts per square meter. Okay? And the answer you get is that it's 500 watts per square meter. That's one thing I could have asked you here, one thing you could be asked on the exam. However, I'm not asking for the exact intensity value. I'm asking you for what percentage is left over. So easily, you have 500 out of 1,000, it's a half. It's essentially just that number there. So this is 50% of your original intensity. Okay? So that's what we're asking for there. So for this one, we're just going to say it's B, 50%. So notice so far, it does not depend on the angle that we were talking about, that 60-degree angle. So it has no dependency on that. And that's just simply because we've gone from unpolarized to polarized. It will always be 50%. Now, 16, I'm asking you now for what percentage of intensity, again, compared to the initial unpolarized light, remains after the light goes through the second polarizer. So upon going through the first polarizer, you have an intensity I1, which is 500 watts per square meter. Okay, so 500, I'll write 500 watts per square meter. I'll suppress the units, but we said that this was 50% of what we had here, which was we had 1,000 watts per square meter, or 100% of our light. Okay. Now, as this light passes through the second polarizer, we only have this much left, so we're going to lose some when we go through this polarizer here. Now, it depends on the angle, and that's where we're going to use Malice's law. So Malice's law states that the intensity out equals the intensity in times cosine squared of that angle. Okay. So in this equation, again, the intensity in is just the intensity of light that immediately goes into that polarizer. So with this second polarizer, the intensity in is actually I1, and the intensity out, we'll call it I2. So now the angle that you plug in, so theta, is defined to be the angle between the orientation of the incoming light. So the incoming light to this polarizer is vertical. Okay. The angle that that transmission axis makes with this vertically polarized light, in this case, the angle between that is 60. So we actually do use the 60 here. But you should always remember that it's the angle between the transmission axis and the orientation or the polarization of your incoming light. So angle between incident light polarization. Okay, so the reason why I'm stating this very generally is because the light didn't have to be vertically polarized. That light could have been horizontally polarized, and that would have changed what you would have done. So it's the angle between that and the transmission axis of that polarizer. So in our case, I'm going to write that this light that goes through this polarizer, so what will happen is this already polarized light will become repolarized in a different direction. In other words, if it starts out with vertical orientation, it's now going to align itself with the new transmission axis, so the light pops out exactly like the transmission axis. Now, we'll lose some intensity though, so I2 will be even less than I1. So what we're going to say is that I2 equals I1 cosine squared of theta, and we'll plug in the angle of 60 degrees into here. Now, again, there's two ways you can look at it this way. You can either calculate the intensity of that light, like we did here, which was 500 watts per square meter, or you can find a ratio, which is your percentage. So let's say that you calculate this out. So I2 equals I1, which is 500 watts per square meter, times cosine squared. So remember that when you take the cosine of 60 degrees, you get a value and you have to square it. I'll actually write it this way: cosine of 60 degrees squared. Now, the cosine of 60 degrees is actually a half. So if you plug in the calculator, it's just 0.5. But you square it. So instead of a half, it becomes a fourth. So actually, we have that it's a fourth of 500 watts per square meter, which gives us, if you cut that in half, it's 250. And if you cut it in half again, it's 125. Okay. Now, that 125 that we have left, so 125 watts per square meter, the percentage that we care about is the percentage compared to what we had originally, which was 1,000. So if we divide 125 into 1,000, it's actually 12.5%. Okay. So we have 12.5% of our original light left over now. The other way you could have looked at it was that you didn't need the 500. The only thing you needed was this fraction, because this fraction tells you that you're only taking a quarter of what you put into it. In other words, you're only taking 25% of it. But the answer is not 25% because you only had 50% to begin with going into it. So 25% of 50% is 12.5%. Okay. So, yeah, so the worst questions that I can actually give you are percentages. So if you can get how to work with the percentages, that's the hardest case with these. So let me know if you have any questions, and we'll go from there. So first question is, wouldn't it be 30 degrees? So no, because I screwed up the wording. On here, change the wording from horizontal to vertical. It is 60 degrees with respect to the vertical instead of horizontal. If that's the case, the light that, comes out of the first polarizer is vertically oriented. And that vertically oriented or polarized light comes into this second polarizer with its transmission axis, which we're going to say is 60 degrees from the vertical. So in other words, it's 60 degrees from the vertically oriented light, which is the angle that you plug in. So it is 60. So for 16, so let me run through this. So 15 we said was 50%. 16 will be, the closest answer is 13%. I'm rounding to that. So it is D. And then another question is, could you show how you mathematically got 12.5%? Absolutely. So actually, let me write that out here. Okay. So let me use this space to do it. So way 1, you can say that I2 divided by I0 is 125 watts per square meter divided by 1,000 watts per square meter, and then that'll get you 0.125, which is 12.5%. So you can either do that, or 2, you can say that in here, if you do not plug the intensity in other words, you leave it as I1, so I2 equals I1, and what I'm going to do is on the cosine, you still plug in the angle, so you say cosine of 60 is a half. You square the half and you get a fourth, so it's times fourth. Okay. If you want to do this, then what you can say is, well, there's another equation for I1. So for instance, I1 equals 1/2 of I0. That's what we said when we went through the first polarizer. The first polarizer only took half of its intensity away because you're going from unpolarized to polarized instead of going from polarized to a different polarization. Okay. So when you plug in this here into I1 and you account for that 1/2 initially, you get 1/2 I0 times the 1/4 you got, and that equals 1/8 of I0. So this fraction right here, actually, let me erase this. 1/8 is 12.5%. If you want to finish the job here, I2 equals this. So in other words, if I wrote that I2 equals 1/8 of I0, and I just divided off I0, it says that I2 divided by I0 is 1/8, which is 0.125. Okay, so when you take I2 divided by I0, that's what we did here. When you take the final intensity and you divide it by the initial intensity, and here there are exact values, you get 0.125, and that's what you get here. When you take the final intensity and you divide it by the initial intensity, you get 0.125. So that's how you do it both ways, with numbers and with just the ratios without plugging in the intensities. Does that make a little bit more sense? Okay, so that's a good question. Why would you not divide 125 by 500? That's because we're not comparing the 125 to the light that came into that second polarizer. We're comparing the light that's coming out, the 125, to the very, very start of the problem. In other words, I want the percentage of the original light before it entered any polarizers. So if I asked you instead, what percentage of the light is left over after you go through the second polarizer? So what percentage pops out here from that second polarizer compared to what went into it? You would be correct. You would divide 125 by 500. But because I want what it is compared to the initially unpolarized light, since we're doing that, we have to compare it, the output, to where it was at the start. So what you're asking could be correct if the question was different. And then you want to explain what it means by vertical and horizontal with this problem. So let me give you a very short hypothetical and then we'll move on from here. Let's say hypothetically erase this, and why don't we just erase all this? Okay, so hypothetically, what I could have done is I could have had the first polarizer have its transmission axis be horizontal. Okay, so the transmission axis is horizontal. I'm just drawing it with a little tilt because it's three-dimensional, so it's a little perspective, but it's horizontal. The second polarizer has its transmission axis, which will be in the same orientation as the problem, so 60 degrees from the vertical. So if I drew a vertical line, I'm saying that the transmission axis is 60 degrees from the vertical. Okay. Now, where that will affect your answer is that when you go through this problem, so you have your initially unpolarized light, it goes through the first polarizer, but it's not going to be vertical now. This light going from unpolarized to it's going to be polarized now, it will be horizontally polarized. So in other words, its electric field, its polarization matches the orientation of that polarizer, so it's horizontal. Now, would that affect the answer to the intensity? No, because anytime you go from unpolarized to polarized, you cut it in half automatically. It doesn't depend on the orientation of this. If you go from unpolarized to polarized, it's a half of the intensity. Now, if you repolarize the light, so if it's already polarized in one single direction and you repolarize it into another direction, that changes the answer. So then here, because I said that the angle theta is the angle between the polarization of that light, which is horizontal in our case, and the transmission axis, which is not 60 degrees from the horizontal, but 60 degrees from the vertical, you need to change it to 30 degrees from the horizontal, because it has to be the angle between the transmission axis and the polarization of the light, which is horizontal. So in that case, you would have used 30, not 60. Okay. So that's how it would affect your answer if I said something was with respect to the horizontal or with respect to the vertical. So you have to pay attention to what the angle is between what and what. So, are there any other questions with the polarizers? Hopefully that made a little bit more sense, maybe. Perfect. Now, there is one last question to this. You said, so what is the transmission line? So a brief description of what the transmission line or the transmission axis is the axis along which it will allow an electric field through for the light. So if you refer to the orientation of the electric field as the orientation or the direction of polarization of the light, it is just simply the line along which the polarization will be permitted through. So if the line is horizontal, that means you can only have electric fields or polarizations that align horizontally. So whatever pops out has to match the same direction as that axis. So that's in summary what the transmission line or axis is. If you want to go into details, so if you do more stuff with optics, if you will, whatever field you're choosing to go into, and you deal with polarizers and polarized light, you might have to talk about some of the properties of the polarizer, which there's essentially molecules inside the polarizer that have properties that make it so that the electric field will only align in a certain orientation out on the other side. So there's a whole field of study of optical properties of materials and how light interacts with materials. So yeah, it's pretty cool. In case you are interested, I would suggest looking up what's called optically active materials. If that falls into your field of study, that might interest you. Now for 17, Suppose that the second polarizer is rotated until its transmission axis is perpendicular to the first polarizer. Okay, so what does that do? So the same question is, what is the percentage of the intensity that exits out? So the thing is that, oh, I didn't switch it over. There's the question. So if you rotate it until its transmission axis is perpendicular to the first polarizer. So you have two polarizers with their transmission axes perpendicular to each other. So what happens is, let me use this diagram. So let me just redraw this out. So regardless of this first polarizer, regardless of its orientation, we know that it's going to become polarized in the same direction as the axis. Okay, so we can assume it's horizontal, we can assume it's vertical, it doesn't matter, because in the second polarizer, we know that regardless of its orientation, it's perpendicular to the first orientation. So if this one was horizontal, this one's vertical. If this one was tilted at some angle, well, this one is the same angle plus 90 degrees. It's perpendicular. So why that's significant is because if this transmission axis is perpendicular to this one, which is the same thing as saying it's perpendicular to this polarization of light, well, if it's 90 degrees between them, well, angle being 90 degrees implies that cosine of 90 is 0. So in other words, there's no transmission at all. Nothing transmits through the polarizer. So what do you get over here? You get nothing. Okay? So there is no transmitted light on the other side of this when its transmission axis is perpendicular to the light that goes into it. So that one's pretty simple when you realize that the angle is just used as 90 degrees in the equation. So it's 0%. So the answer for this one is E. All right. We're getting to the last stretch of material, so looks like we're doing relatively good on time. Okay, so now we're going to move into reflection and refraction. So for questions 18 through 20, so the next 3 questions, we consider an incident light ray. So we have this ray of light. It travels from Earth's atmosphere toward a frozen lake at a 45-degree angle with respect to the normal. The normal meaning this line right here that is perpendicular to the surface. If it's not drawn, remember it's the perpendicular line to the surface that you're talking about. So be careful with this, because you need to make sure that when you deal with particularly refraction, remember the angles that we use for Snell's law are always with respect to the normal. So if I told you an angle with respect to the surface over here on the left side, you would need to translate that over to the other angle between that ray and the normal. In this case, it's 45 degrees, and I give you that. So I give you 4 different ray paths. So ray 1, 2, 3, and 4. I also give you the indices of refraction for different materials, including air, ice, water, glass. So in this one, the first 2 are a little more conceptual. You can calculate things and you can figure this out if you want to, but these are just conceptual, so they're easy, relatively. For the reflected ray, I want to know which one of these 4 is the reflected ray. So very easily, the ray comes into the surface from left to right, hits the surface, and it bounces back, just like Big Sean. If you get that reference, good for you. So ray 1 is the reflected ray. So the answer is A for that one. For 19, we want to know which ray is the refracted ray. So the refracted ray is the ray that goes through or transmits through the surface. So from the incident ray goes to the surface, and it penetrates through the surface, and we have to determine if it's ray 2, ray 3, or ray 4 at that point. Now, it can't possibly be ray 3 because ray 3 doesn't bend. Refraction deals with the bending of light upon entering a different kind of material. So as long as you're entering a different material with a different index of refraction, that light should bend. So it cannot be 3. So the question is, does the light bend more to the right, in other words, away from the normal, or does the light bend towards the normal? And that has to do with if you're going from a low index to a high index, or if you're going the other way around. In this case, because you know you're going through Earth's atmosphere, which is air, the index is 1, you should know that without us telling you. You're going into a frozen lake. That means that it's ice, which is 1.31. So you're going from a low index of refraction, where the incident ray is, towards a high index of refraction. And you should know conceptually that the light bends towards the normal. In other words, from ray 3, which is where it would have gone without bending, and it bends towards the normal, to where ray 4 is, roughly. So the answer for that is D, ray 4. Now, even if you did forget that conceptually, the next question is going to definitely assure you that it's going to be ray 4. Question 20 is, I want to know what direction, or in other words, what angle the refracted ray travels at with respect to the normal of the surface. So this is a calculation. Since it's a refracted ray, we will use the law of refraction, which is Snell's law. Snell's law states that, I'll write this out, N1 sine of theta 1 equals N2 sine of theta 2. Okay, so notice the symmetry to this equation. Both sides of the equation look pretty much identical. You're just calling one side 1 and you're just calling the other side 2. Since they look identical, it doesn't really matter what you call 1 and what you call 2. As long as you're consistent, that's the only thing that matters. So for our case, I'm just going to say that the air above is going to be N1, which is 1, and the ice beneath is N2, which is 1.31. Okay? You can flip them, it doesn't really matter, just be consistent. So the ray enters in like this. The normal line is here. So this angle, you know, theta 1, theta 2, remember they're all with respect to the normal. You have to use it from the normal. So from the normal to my incident ray, that's going to be theta 1, and that's going to be 45 degrees. That's given in the problem. The refracted ray will bend. We expect it to be towards the normal. So if it's toward the normal, the angle here, which is theta 2 is going to be smaller than theta 1. So if you get an answer that's larger or equal to 45, you know it's not correct. So we're going to solve for theta 2. So we divide by N2 over to the other side. So N1 divided by N2 sine of theta 1 equals sine of theta 2. And then we take the inverse sine of both sides to isolate the angle. So theta 2 is the sine inverse of all the other stuff, which is N1 over N2 sine of theta 1. Okay. So we just plug into all of this, so we get the sine inverse of N1, we said was air, which is 1, divided by N2, which is ice, which is 1.31, and then the sine of 45 degrees for our incident angle. So theta 2 is, so sine of 45 is 0.707. If you use that a lot, you tend to remember the number. Times that over 1.31, so we divide by 1.31, and we take the inverse sine of that. So the inverse sine of that will give us precisely 32.7 degrees. Okay. And we need to be a little bit more accurate because the index of refraction for water, if you made the mistake of using water, the angle is very close to this, but a little bit different. So it's 32.7. So notice that 32.7 is smaller than the 45 that you started with, so it does indeed bend towards the normal. Okay, so ray 4, that's correct. Ray 4 was the ray for the refracted ray. So ray 4 for the refracted for 19. And then for this one, we got 32.7, so that's C. Okay. You want me to explain again why the refracted ray would bend towards the normal conceptually in ice? Okay, if you're looking for a conceptual reason, here, let me give you a brief overview of what happens with that. It's hard to explain it conceptually. It's more so with the equation that you can determine that. So in very short and sweet and to the point, if you use the equation, the angle gets smaller when you go from a low index to a high index. So from air being 1 to ice or something else being larger than 1, when you go from low to high, it bends towards the normal, and you can calculate the angle and you can find that it's going to be a smaller angle. Smaller angles in this diagram means that it's closer to the normal. So if that doesn't satisfy you, then here's a little bit more of a conceptual detail, which I won't go into depth with because it's a little bit more beyond the scope of the class. But you can think of it this way. Here's like a little analogy. Is if you had like a lawnmower, and here's the two front wheels on the lawnmower, and you drive the lawnmower from, like, this could be like concrete, and then here's the grass. Okay, well, the grass tends to slow you down. Okay, so when the lawnmower reaches the grass, what happens is that the front, one of the front wheels reaches that boundary first. So what happens is it slows this wheel down, but this wheel keeps on going more distance, so it goes faster over here. So what it does is it rotates the lawnmower and it causes it to turn this way. Okay, simply because one end hits it first. So when you go from a faster medium to a slower medium, what will happen is it bends in towards the normal. Now, this is only an analogy because it's light. Light doesn't have wheels. Light doesn't, it's not like a lawnmower exactly. But you can almost use this conceptually to help you understand that when you go from a faster medium to a slower medium, the light bends towards the normal just like this would. So in this case, the faster medium would be like air, vacuum, because there's nothing there. The light can travel freely. But when you have a bunch of stuff in the way, a bunch of molecules from like ice or glass or whatever those molecules are, it will slow it down more and it will bend it more towards the normal. So that would be the more full conceptual reason about why that happens, but that's more complicated. Yeah, if you need to head off for the night, then good night. And you can rewatch this tomorrow morning, but we'll probably finish in the next 30 minutes or so here. If no material, quote unquote, is given for N1, we just assume it's coming from air. Yes. Now, I would say yes 95% of the time, because in most circumstances you would have a case where, let's say light enters a lake, okay? If I tell you that light enters a lake, then the picture that you should probably draw is you standing at the edge of a lake, and of course you're in air. So that's why I would say most of the time it's air. Now, if you're a fish in the water and you send a light ray from where the fish is out of a lake or whatever, so I guess technically even in that case it would still be air on the other side, so yes, you would still assume it's air. Now, the reason why I say it's only 95% of the time is because you can have circumstances where it's like, okay, what about if light goes from outer space where there's nothing at all, not even air, and the light goes from nothingness, also known as vacuum, to the Earth's atmosphere, which is made up of air. Then in that case, you would do a Snell's law from vacuum to air, which would almost make no difference, but notice that actually the index of refraction for air, even though we say it's 1, it's technically 1.0003 or something. It's so small that we call it 1. But if you're doing experiments and you're doing things with like NASA and you need to be precise, it's not quite 1. There are certain special circumstances in which you will have no assumptions be made, such as being precisely told that it's vacuum and air. So pretty much in this class, yes, assume it's air or vacuum, either or, because we use 1. Are there any other questions on the laws of reflection and refraction? No problem. All right, let's carry on. 21 through 24. Which, by the way, a little fun fact, if you did get a little curious about what I was just talking about, a perfect example of using the law of refraction with like outer space and Earth's atmosphere is the rays of light from the sun entering the Earth's atmosphere, and the light actually does more complicated things, but the reason why sunsets and sunrises look the way they do have to do with the way that the light bends and scatters through the atmosphere. And also the same reason why the moon turns red during a lunar eclipse has to do with the fact that the light actually refracts through our atmosphere and bends around the Earth onto the moon. So that's a little fun fact. For these questions, we have a spherical mirror. So you can already see here that the mirror sticks out to the left towards the direction of the light, which means it's a convex mirror. Now, I tell you that you have the height of the object. I tell you that we hold it this distance away from the convex mirror. So the distance between the mirror itself and the object is 3.75 centimeters. The radius of curvature is given to be 7.5 centimeters. The center of curvature is marked as point C in the diagram. Now you could eyeball this because I'm telling you the figure is to scale, which means everything you do can be treated precisely, but you should be able to determine that P3 is halfway between the center of curvature and the mirror regardless. So which point is the approximate focal point of the mirror? That one's an easy one. The focal point of a spherical mirror is approximately half of its radius of curvature. In other words, the distance between the mirror and point C, cut that in half, and you get to point P3. That is the focal point of that mirror. So point P3. This one you have to do a little bit of work for. There's actually 2 ways to get the answer to number 22. I want you to use a ray trace for this, but we're going to check our answer with the math. So we'll have 2 different ways of arriving at the answer. So we need to find where the image forms. In this case, we're going to do a ray trace. So let me draw this out and let's ray trace this. So let me try to do this as best as possible. So what I'm going to do is, now if you do this on an exam, you'll probably have everything already sketched out for you enough that you don't need to worry about this. But if you start the ray trace from scratch, draw a perfect circle as best as you can, and then you basically cut it in half into whichever side that you want to use. So for instance, the convex, we'll use the left half of it. So we erase the right half, and we fill in the left half. In case you need a proper technique to draw a perfect circle, refer to the SpongeBob episode where he draws the head and he erases all the details out and gets the perfect circle. So that's how you do it. Now we have a convex mirror. And I'm going to draw this axis down the middle, which perfectly cuts it in half. It's a line of symmetry. Okay. The center of curvature was roughly about here when I drew this. Label it C. And now if you look at the diagram in the figure, do pay attention to the fact that everything is pretty much equally spaced. So P1 to the mirror, to P2, to P3, 4, and in the center of curvature, they're all equally spaced from each other. So that will actually really help you to figure out what needs to happen. So here, P3, P4, P2, P1, and the object. So now the object is over here. Object I'll label as O. Now, I will use 3 rays at minimum to do this. When you're doing a mirror ray trace, you should use 3 rays. I'm going to do the parallel ray, which will start from the top of the object, and it will go to the mirror like this. Parallel. It's parallel to this axis of symmetry here. So it pretty much is flat. Now, this ray, because the light is not allowed to go through the mirror, the only thing that ray can do is bounce off the mirror. But I want you to note that the parallel ray will bounce off in such a way as to go away from the focal point. So if you had the concave mirror, which is the other half of the mirror, what would happen is the parallel ray would bounce off the mirror and it would bounce back and go through the focal point. But in this case, the parallel ray will bounce off the mirror and it will actually go directly away from the focal point. So if this is your focal point right here at P3, so I'll actually just label that as F, then you can almost draw this line of sight that goes straight to where the parallel ray hits the mirror, and you just continue it out like this. And that's the direction that the ray actually reflects off, but this line indicates the direction that it came from. So make sure to draw this dashed line in. That's the most important thing here because it's going to intersect with another ray. Now, this is actually where the mirror gets its name from, so not the convex, but it's also referred to as a diverging mirror. And that's because parallel rays diverge or spread away from the focal point. So another easy ray is you could do the center ray or the center of curvature ray, which is aimed directly at the center of curvature. So this one will be aimed straight at point C, but it won't go through to point C. It's just aimed over to there. Now, if you continue the direction in which it's aimed by drawing a dashed line here, you'll find this point of intersection. But let's keep on doing another ray to find out if that's really the point. So I'm going to use what's called the midpoint ray. The midpoint ray will go from the top of the object, hit the midpoint of the mirror, also known as the vertex. It will go to the vertex and bounce off at exactly the same angle that it came in at. So you have to then take that angle and do the same angle below, like that. Now, if you do it, with a little bit of care, Now, because this ray doesn't intersect with any of the other rays, you know, just like this one didn't intersect with that one, you have to trace it back where it appears to come from. So if you're on the left side and you're looking into the mirror, you see this light ray coming out at you. So you can trace back where it appears to come from, and notice how it crosses at the same point there. So that's already enough information to be able to say that the image forms right there. Now, the last ray will be the focal ray if you choose to use it. You only need 3 rays, so you only need 3 of these 4. But the focal ray goes from the top of the object, is aimed at the focal point, but cannot reach it because it hits the mirror first. But the focal ray will always do the reverse of the parallel ray. So the parallel ray comes in parallel and then comes out away from the focal point. This one is aimed at the focal point and it comes out parallel. So it comes out like this, roughly. And if you trace it back where it came from, also intersects at that point. So the image forms here. You draw the image starting from the axis of symmetry and you draw up to where the intersection point is. So that's your image. Label it as I. From your ray trace alone, now there's a couple of things you can figure out. Number one, the image more or less forms around point P3. I guess when I wanted you to find the exact point that this forms at, I would say if you were doing this on the test and I gave you P2 and P3 as an option, P2 and P3 are both probably acceptable answers in this case. I probably would have just said between P2 and P3. So P2 or P3. Okay. Now, you can also figure out what the description of the image is in this case, which is actually what I ask you next. So if you look at the next questions, okay, so here, the approximate position of the image, I'm going to say that you're allowed to say either P2 or P3, and that's fairly good. If I were to actually probably word this better, I probably would have just gave you options that said between 1 and 2 to between 2 and 3, etc., and that probably would have been better. What describes the final image? So if we go back to how this looks, there's 3 types of descriptions. You can talk about the type of image, which is real or virtual. You can talk about the orientation, which is it upright or is it inverted or upside down? And you can talk about the size of it, which is either reduced or enlarged. So in this case, the type is virtual because these rays are not actually here. You have to look into the mirror to see where the rays come from to then see the image, so it's virtual. You then say that it is standing upright, and it's obviously smaller than the other one. Now, if for some reason you can't tell if it's bigger or smaller, you can also look at the distance from the mirror. The one that's closer is the smaller one. So in this case, it's reduced. Okay, so there's your image descriptions for this one. So the answer to this is that it is real, upright, oh no, virtual, there we go. Virtual, upright, and reduced. So the answer is B. All right. Any questions up to 23 before we do this last one with this? And then we'll be on the last stretch of questions. Okay. Was 22 B and C? Yeah. So I said either B or C would have been good enough for this one. If this were more properly written, if I thought about it at the time, I would have actually just said an option would have been between P2 and P3. So B and C in this case would be acceptable. Convex mirrors create real images and concave. No, so no, there's two things about what you're saying. So if you're saying convex mirrors create real images and concave create virtual images, that's not true. Because so first of all, it would be flipped if anything. So if you look at this here, this is a convex mirror. Okay, so the convex mirror creates a virtual image. Now there's only one case for this mirror. No matter where you put the object in front of the mirror, there is no special points that you pass over. And by special points, I mean the focal point or the center of curvature. If you do not pass over the focal point or the center of curvature as your special 2 points of interest, the image type or image description does not change. So no matter where you put this object, it never crosses any special points. It will always be this description. So therefore, for the convex mirror, not lens, the convex mirror produces virtual images only. Now, for the concave mirror, this is why I'm going to say, even if you wrote that correctly, based on what you said, even if you wrote that the other way around, it's not necessarily true that concave mirrors produce real images. They can produce real images, but they also produce virtual images too. So, for instance, I'll quickly sketch it out here. I'm going to erase this, so let me see if anybody else has anything. Looks like we're okay. So I'll quickly sketch it out. I won't do the full ray trace, but I want to quickly show you that the concave mirror is capable of producing both kinds of images. So when you do the concave mirror, here's a rough sketch. You know, here's the object. Let's say here's the center of curvature. Here's the focal point. Okay, so the object is outside of the center of curvature and the focal point. So if I were to do a quick ray trace without much explanation, I can show you real quickly. Parallel ray out through focal point, and midpoint ray back out like that. I'll do one more ray. I'll do the center ray. Okay, so then, okay, so here's the point of intersection. There's your image. Notice that the light actually does cross here. The rays actually do cross here. You don't need to trace them back and see where they appear to come from. This produces a real image. Okay, so concave mirror, yes, it can give you a real image. However, it can also give you a virtual image because when you, so concave, center of curvature, focal point. Okay, so let's say if you stick the object inside the focal point, this is what I was talking about earlier, where if you move the object around a critical point such as the center of curvature or the focal point, it does change the image description every time you skip over one point. So if you do a ray trace here, for instance, parallel ray goes out through focal point, and you do, let's say, the center ray. This one has to go through the center first, through the top of the object, and you have, let's say, the focal ray, which has to go through the focal point first, then through the top of the object, and then out parallel. If you do this, all three rays don't cross in this space. You have to trace them back so that they all can cross, and by doing that, you'll find that the image actually forms back here. So the image forms there, but the rays don't actually go back there. So this case is virtual, but it's the same kind of mirror. So concave mirrors can produce both types of images, real and virtual, and convex mirrors can only produce virtual images, no real images. Don't associate that also with lenses, because the lenses work differently. So that's a different story for lenses. The last question on this, you may or may not have seen this question before, but it's a relatively simple one. It's just you may not have seen it before. If an object is moved very far away from the mirror, so when we say very far, we're talking about the distance away from the mirror is so large that you might as well call it infinity. That number, whatever number you choose to use, that number is significantly larger than any other number you use in the problem. So you call it infinity. What is the approximate position of the image? So where does the image form? So in this case, I do want you to calculate something, but the calculation is actually really, really simple given that you know that the distance essentially goes to infinity. There we go. Whoops. Okay, so if you're trying to calculate the image position, then you can use that equation that accounts for the image position and the focal length. So 1 over f equals 1 over do plus 1 over di. So you use the mirror equation, which is the same as the Lenz equation. You solve for di, but the thing is that the object distance is very, very, very large. When you put 1 over a very, very, very large number, it practically is 0. So when do goes to something very large, this is approximately 0 because the object distance approaches infinity. And if you do that, it actually becomes very simple. 1 over the focal length equals 1 over di. So therefore, well, approximately, the focal length is approximately the image distance. So the image forms roughly at what the focal length is. So if the focal length of the mirror is, well, I told you in this problem that it is, what is that? The radius of curvature, so I actually didn't tell you the focal length. I told you the radius of curvature is 7.5. So that being the case, that got out of the picture 1 second. There we go. If I told you the radius of curvature is 7.5, then the focal length is half of the radius of curvature. But you need to be careful with that, though. The thing is that the focal length is half plus or minus. So for our mirror, which is convex mirror or a diverging mirror, the focal length is negative. So the focal length is negative half of 7.5, which is, so let me write this out. It's negative 7.5 centimeters divided by 2, which is negative 3.75 centimeters. Then the image forms at approximately minus 3.75 centimeters. Yeah. So this is an example of using this equation, but this is a very special or unique circumstance that is good to know. So let me know if you have any questions on that, and we'll move on to the lens, and then we'll be done. Okay, so then let's see, how did I get the 2 in the denominator? The 2, you talking about for the focal length? Yeah, the focal length is the radius over 2. So what I meant was the focal length equals minus the radius of curvature divided by 2. And it's minus because it's a diverging mirror, which in this case is it's a convex mirror. So the focal length is always positive if the system is a converging system, and the focal length is negative if it's a diverging system. So for mirrors, that means that, so for mirrors, okay, convex is a diverging system, which actually means the focal length is negative. The concave, the rays actually cross and converge at the focal point, so the focal length is positive because it's converging. When we do the lenses, okay, if you choose to talk about convex and concave, so a double convex lens and a double concave lens, you have to be careful about that, because the double convex is actually going to converge the rays, not diverge the rays, which means that the focal length is positive as opposed to the convex mirror, which the focal length is negative. So you have to be careful. And then the double concave, the focal length is negative because double concave lenses actually spread rays apart on the other side, so it's a diverging system, and that makes it a negative focal length. So note the words convex and concave and how the signs are actually switched for lenses. So all right, and these will be the last 3 questions. So yeah, no problem. Okay, for questions 25 through 27. We have an object which is held 20 centimeters away from the middle of the lens. I actually give you the ray trace in this picture, interestingly enough. Now, you can treat this as a ray trace that you ought to know, basically. There's a number of ray traces that you should know for the different cases of the mirrors and the lenses. This is just one of them. This orange ray right here is the parallel ray. The red ray is the focal ray. Notice how it aims somewhere and comes out parallel as opposed to this one going in parallel and then spreading out. And this one that cuts perfectly through the midpoint of the lens is the midpoint ray. Now, from this ray trace, you should already be able to see that, okay, the image forms right here where all the rays cross. However, you do notice that some of the rays are not technically there. They appear to trace back to there, which means that this image has to be virtual. Now, the other descriptions, so if I drew a little image with a little arrow pointing up to it, that would be upright, and it would also be reduced because it's smaller than the object. So it actually already answers the first question, 25. The image description will be virtual, upright, and reduced for the diverging or the double concave lens. It turns out if you use a double concave lens or a diverging lens, it's always going to be this kind of image. You cannot possibly get any other image type out of that. You cannot produce real images with this kind of lens. It has to be the other kind. The other two, we're just going to make a couple of calculations. So I want to know what the image distance is. Now, in this case, because I give you the object distance, and I give you that the image is 60% of the size of the object. In other words, I'm giving you the magnification is 60%. That doesn't mean that m is 60. It actually means 60 as a decimal, so 0.60. So let's use that information to calculate that out. So let's write out the magnification equation. Okay, so the magnification, there are 2 ways to write it. The definition of the magnification is how big or how tall is your image compared to how big or tall is your object. That's just the definition. but you can also equivalently say it's negative image distance divided by object distance. So in this case, I am going to use this part of it because I want to solve for my image distance based off of my object distance, knowing the magnification. So we start out with m equals negative di divided by do. We solve it for the image distance, which is negative the magnification times the object distance do. The magnification, we said, was 60%, so that means it's 0.6. Now, you do have to be careful because just because the size is 60% of the object, that doesn't mean I'm telling you if it's upright or inverted. Because if it was inverted, you would use negative 0.6. But since it's upright, you use positive 0.6. So remember the magnification, the sign of it determines if it's upright or inverted. The actual absolute value, in other words 0.6, is just how much bigger or smaller it is. So if the magnification was 1, it means it's the same size. So if you're larger than 1 or smaller than 1, absolute value, that tells you if it's larger or smaller. So I'm going to use positive 0.6 to represent 60%. And the minus sign was from the algebra, not the magnification. DO is 20 centimeters in this case, I think. Yeah. And we take 60% of that. So we're going to get 0.10 plus another that. So it's, what is that? Negative 12 centimeters for our DI. Okay. So the image distance is negative 12 centimeters. Now there's a couple of things out of this, but one of the important things to note is that the negative sign indicates that it's a virtual image. So minus implies virtual. Okay. Positive implies real. Okay. So the answer to this is negative 12 centimeters. That's B. And we have our final question here, which is to just find the focal length of the lens. So the focal length of the lens, we have one other equation we can use, which is the Lenz equation, the same as the mirror equation, which is that 1 over the focal length equals 1 over dO plus 1 over di. We have both dO and di, so we can plug that in. So it's going to be 1 over positive 20 centimeters plus 1 over di, which we found to be negative 12 centimeters. Now, before you even get the focal length, you should expect that the focal length be a negative value because it's a diverging lens. Diverging systems have negative focal lengths, so this kind of lens should have a negative answer. And let's see what we get. 1 over 20 plus negative, so we're actually subtracting 1 over 12. Now the answer you get is negative 0.03, but that's before you flip it because it's 1 over f, so don't forget to flip it. And we get negative 30. So the focal length is negative 30 centimeters. Okay. And the answer to that is then B, negative 30. Okay. Are there any other questions on the set of these 3 questions before we head off? And then, so tomorrow, my usual time, the usual place. And so 1 o'clock till 3:30. And what we're going to do is we're going to go over one more version of this. Now, what I'll do is I'll probably make it, it'll be a little bit more similar to this version because it's got more multiple choice, and that's probably more or less what you'll see on the exam. I can't make too much modification to it in the amount of time I have, so I'll modify as much as I can in the time that I have, and we'll go over a final version tomorrow, and we'll review more concepts in depth. We'll do more ray traces if you want to, and I'll answer any other questions that you have. But let me know if there's any other questions before we head off for the night. Thank you. I don't think of myself that way, but I always try to do my best for people. Looks like we're good, so yeah, no problem, and thank you all for tuning in. This was my biggest live stream yet, so yeah, we'll go from tomorrow if I see you tomorrow, but otherwise best wishes if you're studying for your exam. So you're welcome, and have a good night.